So hi everyone, welcome to the second lecture. Last time we talked about trichomes, and I promised to prove the existence in two different ways. I intend to keep the promise. So the first proof for the existence of trichomes will be based on the Lovasz Local Lemma. So again, I'm only doing that in order to demonstrate like non-trivial tools from probability theory, being used for the probabilistic stuff. So the Lovasz Local Lemma, I think it should be like something like that. The Lovasz Local Lemma tells you something like that. It tells you, say you have a bunch of events, and you don't want any of them to happen. Okay? So let's A1 to AN be events. Yes.
אתה יכול לסגור את הדלת כדי ש...
So that they want the event. Again, you should think of these as events you want to avoid. And okay, so for example, by the union bound, if you know that each of these events has a low enough probability, in particular, the sum of probability is smaller than 1, you are happy. Right? It means that there is a point in the sample space which avoids all bad events. That's the union, by the probability that the union of those happens is at most the sum of the probability of events, which completely ignores, by the way, all correlations or dependencies between the events. That's part of it. But sometimes it doesn't, it's not enough. And this is where the discount. Other levels, but this is a particular important example. So say you have these events, and let's say that they are independent, but only to some extent. That's where the local comes from. So say AI from I is mutually independent, and I will say exactly what I mean by mutually independent in a second, but essentially think of it independent of not all of them, but of all events outside of some subset that's denoted by gamma. Okay, so gamma of AI is just a subset of these events, and I'll formalize that in a second, but essentially think of AI as being independent of everything that's outside of it. Right, so again, I'll define in a second what mutually independent means, but let's keep it like on an intuitive level. Then, again, what you want in the end is to say that there is some non-zero probability in which none of these events happen. You want to avoid all of them. So I want to give you the condition which you actually need for the proof of the existence of trichoid, but it's slightly tricky. So I will first give you the easier, which won't be sufficient for us, but just to state it, the easier kind of variant of the Lovasz Local Lemma. So there's going to be two bands. Band, and this is called the symmetric version. So assume each event has bounded probability of occurring. Right, so you want to avoid all of them. Definitely, you would expect that there is some condition of that form. You want to avoid all of them. Is that PI or P? P. Yeah, for some P, like uniform overlap. And gamma of AI. So again, you should think of it as the number of events that AI depends on. One is this one. One to have many independent things going on. This thing is at most D like 4 degree example. There is in a sense underlying graph here of dependencies which I'm not talking explicitly about. Think of that. Right, so what you see here is that assume that none of the events happen with too high probability, and each event depends on most kind of the events. If, Okay, so EP is E. D plus 1 is at most 1. Right, so E is a constant, you can ignore it for a second, but if these two are not too large combined, like each of these is bad if it's large, because this is the probability of an event to happen, and it's the dependencies which you want to kind of say something even at the presence of these dependencies. Then you're happy. Then there is a non-zero probability for none of the events one. None of the events two. Okay, so assuming each event doesn't happen with too high probability and there are not too many dependencies, you see why I can call it a symmetric version. Every P and D are independent of the i's. And assuming that you can somehow bound P and D, in this sense, then you are happy. Then there is a point in the probability space which avoids all the events. Okay. Non-trivial, not too complicated, but non-trivial. Yeah, you know. More complicated than uniform. The magnitude. Everything is non-trivial. And also just note that this thing is not, I'm not saying that this is close to 1 or something like that, I'm just saying it's larger than 0. 2 is very small, it's still larger. Now, we will actually need the asymmetric version, which is more complicated to state, but I'll have to use it. And in the asymmetric version, you don't, it's not like all events are equal, are the same. So in the asymmetric version, so you can replace this board with that board. So it's this board is common to both of them, but then this is board 1 and 3. The asymmetric version says that say you can label each event with a real number. Let xi, a real number, and technically it's between 0 and 1, half closed, half open. So I think of it as a number associated with the event AI, okay? Be such that, okay. So let me just write it down. So for every I am doing that, and now I'm looking at this condition. So now I'm saying, there will be a van in a second, but so now I'm saying, I'm going to replace these conditions, which are much nicer to look at, but won't be enough for us, with a more asymmetric condition. So say I can associate with each event AI a number xi in such a way that for all I, everything is for all I. For all I, the probability of AI is not too large, but not like P not too large, but rather not too large with respect to the its own xi, and the xj's that the event AI depends on. Right? Because these are all the events that, or the indices of the event which AI depends on. So I'm kind of factoring their xj, or the kind of complement in a sense, in the bound. Right, so for example, you can't take x to be 0 because that will kind of kill you. It will be, I mean, there is some probability for this event to happen, and you want to kind of figure out what are the xi's when you use it. So you can't take all the x's to 0, for example, because that will kill you. Yes. So right. So it's kind of a. So okay. So let me just do it in this string cases. So if the xi's are too small, then you can like xi must be at least like something like that, right? Because this is more than 1. But on the other hand, you can't make them too large because then, well, at least if AI depends on many events, this quantity will be too small, right? Because if there are many events, so if this set is large, so you multiply numbers between 0 and 1 here, and if xj's are large, close to 1, then you multiply many close to 0, say numbers. So there is kind of tension here. So xi is a kind of a blanket over the events in a sense. You can almost see it as like a 1 minus the probability for the event of xj, and so forth. It's really kind of a bound on the probability, but it must be larger. So you can't take it to be exactly the probability. It must be larger to also take into account the dependencies. So so if you think of this as the probability of the AI, I know it doesn't fit, but as a kind of a false guess, then here you get 1 minus the probability of the other ones that it depends on. So whatever this number is, whatever intuition you have for it, it must be large enough to bound that, but not too large so that the dependencies won't get you back. A blanket over the probabilities. It's above them. But then I'll vent the same result. So if you can find these numbers, and maybe in the example it will be more clear, but if you can find these numbers, somehow take into account the dependencies and the probabilities of the marginal and the individual events, then you are happy. This is how. Questions? I'm not going to prove.
Such a function always exists?
No, I know. Yeah, right. So, but if it exists, then there is a right. And in the example, I won't just tell you the function. We can in the keyboard example, we'll actually cook it while we go, and you'll see like at least in that example where the intuition is coming from. But I do have to give you the more information about what is a mutually independent lemma scheme. It's kind of confusing actually. Yes, good. So the second one implies the first one by taking the xi's to be 1 over the difference. You can do the check, and you can see the e coming because we have a product here, and if this set is of size at most d, and this is 1 over d plus 1, you have an e-like expression here. Expression that's of the form. So e is a bound. But it doesn't really matter. I'm just saying that this implies that with all xi being equal to 1 over it. Oh, actually, this might give you some intuition also about the xi's. It should definitely shrink with the number of events that you depend on. But you can see it already from here because of the product. I'm just curious, how many of you ever saw this? I mean, I don't know. You said okay, good. Independent event. That's actually tricky. I actually once got a 98 in 100 in a seminar because I talked about that and I really didn't understand what it means. I didn't even notice I don't understand what it means. And like 15 or 20 years later, I'm okay with it now. But actually, I don't want to give you the exact. I don't want to give you the most general and abstract notion. I'm just going to give it to you in the setting which is always the case, anyhow. So imagine, I'm just going to say what mutually independent means, but in a setting which I'll talk about now. And in this setting, these events are not just like events in a probability space, not just subset of a probability space like events are, but rather you should think of it more kind of in an operative way. So think that, assume that, so blue is for like the notes, the remarks. There is a color system here. Blue is for remarks. You have blue, you can do blue. Yes. So assume that actually all of these events are coming from some underlying set of random variables. So assume you have like random variables, maybe I should include x, R1 up to Rn. Has nothing to do with that n. So these are random variables, okay? And all of these events are actually events with respect to these random variables. Maybe the first event is if all of them are equal. And you're going to assume that they are independent. Okay, so there is some underlying thing which does come from independent random variables, and the AIs are dependent events, but the only dependencies really come from on which random variables they depend on. Right, so each AI is going to depend on some of these random variables. Each AI depends on some subset of this random variable, the Rj where J is in some set. So Si is the set of like indices really of random variables which I depends on. And then that's not the most general thing that you can have, but it's what we'll have. It's really what every time happens. And then you can easily kind of understand what mutually independent means. Random variables. Right. So these are going to be random variables, these are going to be independent. Because the course will take like one more lecture for all the time. But once. Right, okay. Right. So I'm not going to find which I'm going to define mutually independent only in this case. And independent is what you know. It's like they are just independent, like the usual notion of independence. And I'm going to define mutual independence of the AIs only in this scenario where the AIs, each AI depend on some subset of these independent variables. And then mutual independence is kind of obvious. Like so gamma AI is precisely all of those AJs that share a random variable used by AI. Right? So
What is S?
so this is just the step. So for every event AI, we are going to associate a set Si. Si is a subset of the indices of the random variables. Just telling you, really, this just encodes the event AI in which of the random variables it depends. Could be in weird ways. And with that, I think you can see here, with that, you have the gamma of AI. Like this is what I want to kind of define, but at least in this particular case, gamma of AI is exactly like it's all of these random variables, or maybe indices of random variables, or maybe nicer, such that Si, what can you say? So how would you write it? Right.
Yes.
Exactly. Right. So gamma of AI, I'm going to tie my shoelaces here for one again. So gamma of AI is, forget about the general definition. In this particular case, gamma of AI is kind of obvious. Just, you take all the events or indices of the events which share a random variable.
You know, there has to exist these are.
No. Right. So this is called the random variable model. It's more restrictive than general. So the lemma holds in more generality, but then you have to define mutual independence in a subtle way a little bit. Might not be a false guess. So instead, and actually that's what happens in all applications I know, I'm just stating this lemma under the assumption that the random variable model holds. So there are underlying random variables which are independent, and the dependency of the events are actually only coming from the fact that two events use the same random variable.
Mutual independence is supposed to be stronger than
Yeah, it's more general, yes. Right. So depending if you use it or but it's more general. So when you say stronger, it depends if you assume it or use it. So it's a more general statement, and in this random variable model, it's equivalent to that.
So if we say two variables are mutually independent, it gives me less information than if you would say they are.
Right. So for two it's the same. But if you have when I say that one random variable is mutually independent from a set, it's more complicated. Essentially what you need to do is you should partition the set to two parts and show that the probability of the events to happen if the probability of the event to happen assuming this and the negation of that is the same as the negation of that. It's kind of slightly technical, so I'm trying to avoid it.
So your motivation is like to find these M independent variables in order to construct the HI.
Right. So what will happen really, we'll see it in the example, the AIs are actually coming from some RIs. Oh, thanks. It's kind of happen naturally. So that's why it's Maybe you should ask questions.
אחד, שתיים, אתה רואה משהו? אתה צריך לראות בירוק הזה?
אחד. שתי.
עכשיו זה בסדר. עכשיו עדיין צריך. תודה. Any questions about the lemma? Okay. Again, I mean, you'll see in a second where it comes from, but really, you know, if you think about probability theory in general, it's general, an event is a subset of the probability space. But when you actually come across a problem like that, definitely in like combinatorial kind of scenarios, there are actually random variables that generate this. So that's a very useful setting anyhow. Also, it should be noted this is highly non-constructive. We didn't find any problem. This is an existing population. And in the tree code, it's essentially the same. The follows. So let's try to use it in the context of tree code, and we'll see how it relates. Okay. So, right. So remember that the tree code is like an infinite tree with edge coloring, and this is everything is finite. So you can kind of compactify these things, but instead of doing that, I'm going to tell you something which is not obvious, but not surprising maybe. It's enough to construct a frequency for every depth n, even power of 2, with some distance, some uniform distance for distance, 6 colors, but for every n, or any n is a power, which is a power of 2. And if you do that, there is a way of gluing all of these trees. It's not trivial, but all of these trees, one huge infinite tree. And you pay a little bit, the rate deteriorates by a factor of 1/3, and the number of colors by some factor of if you are not shooting for optimal constructions, you can assume that you need to construct a finite depth tree. It's also hard. So can be shown that family is infinite family. Three codes. So one for each depth, and again, it's enough to consider just our powers of 2 if you care about that. But all of them have the same like distance and number of colors. We distance or relative distance delta, everything is relatively different. And C colors. So it can be shown that such a family induces actually also efficiently. If you have the tree codes, you can induces like a legit tree code, infinite tree code as we define it, namely infinite. Yeah. So you kind of glue it together in a way with distance, which is, I don't remember the exact iteration parameter, but omega of delta, you lose some constant factor, and order of C column. So you lose also some constant factor. But it's okay. I'm saying that because I want to apply the lemma in the finite setting, instead of the infinite setting of the lemma. So is it clear? Well, maybe the first thing you would think out. I mean, when you try to do it, it's not the obvious thing or the first thing that comes to mind, but it's really the second. So complicated. So let's just show the existence of that entry code for any n, the number of colors and the distance which are independent. Okay, we want to use the Lovasz Local Lemma, right? So what are the events we are trying to avoid? Right, so we're trying to avoid for every pair of vertices of equal depth, we are trying to avoid this is the least common ancestor, and this is the root of the tree. This common ancestor of U and V. We're trying to avoid many of the pairs here matching for. So our underlying space, these are the allies, the random variables, are going to be, okay, we're just going to assign for every edge a color between 1 and C. These are the random variables. So for every edge, you're going to have a random variable. And for each edge, we have a random variable which is uniform in subset of the integers, maybe 1 up to C. Just, I don't know if you know this notation. 1, 2, C, hopefully 4 in this case. Right, so these are the RIs. So you see there is some underlying set of random variables and they are independent. Because I'm just going to do it independently. But the events depend on the random variables. So the problematic events, and you have one for every pair it will be of equal depth, are, the events are, there are too many matching pairs. Right? So these are the RIs and the AIs. The events are, or maybe I shouldn't call it AI, I should call it AUV to remind ourselves that they depend on a pair of vertices. So the fraction of pairs of the relevant pairs, this pair and that pair, the one perhaps the least common ancestor of U and V and each of UV that has equal color is the most, sorry, it's a bad event, it's more than this is the bad event. For every U and V, you have a bad event. We're kind of breaking down the definition of triggers. For every U and V, you want the fraction of agreements to be small. You want to have at least delta disagreements. So if you have, I should have 1 minus delta, yes? Fine. Okay. So, that has happened when you don't produce it. But if I want to make sure that the distance of the trigger is delta, then the number of agreements should be at most 1 over delta. And the number of pairs, which is the fraction, should be at most 1 over delta. And then you have delta disagreement pairs. And so the bad event is the complement of that. So the fraction of pairs is more than 1. Number of matching pairs is more than 1. And then if this doesn't happen, for every U and V, you got a trigger. Okay? You see, AUV only depends on the colors that appearing here. They don't depend on the colors appearing here or there or the colors on top. It's fine. So what is? Yeah, it's my handwriting. But you see here, the events are naturally coming from random variables that are independent. It happens a lot.
You're not showing us the construction for the 4 color?
No.
That's the object of C.
Right, that's right. This does not give you 4. Even if this would have given you 4 colors, you have these constants. But and secondly, it's an existence of the function.
Is there a construction of 4 colors?
No. So I can give it to you. Right? Maybe there is. Right, let me the existence of this function. Only like increasing polynomial. But the second move that you will see will give you you can easily tweak it. I can actually show you if you get 4, 5. It's better. It's kind of more general. In the second move, I'll actually use the structure. So you kind of expect maybe to do something. Right. But here we are only shooting for like constant number of colors. And let's also just to keep life slightly simpler, let's set delta to 1/2. It's not important. You can immediately see where you need to change the quantities I'm writing here, but just easier to do it like that. Focus on the important stuff. So we are going to construct a 1/2 distance tree for it. So really good distance. 0.1 will be good. But the proof is the same, just a calculation. It's easy. Okay. Good. So you have these events and the underlying unknown variables, and now you want to kind of figure out the dependencies. But the dependency graph is kind of the dependencies are obvious. Right? I mean, when will AUV depend on AU prime V prime?
They have our common
Or they have a common edge. Right. So the only way the event AUV, which really only touches this random variable, right, depends on some EU prime V prime. So I'm using another color, not for just one. So if there are a common edge somewhere, maybe more than one, if there are a common edge, only then there is a they are not mutually independent. Because they're not using the same random variables. Only in this case they're using the same random variables. So the only thing that you should worry about is like maybe to do the same. Maybe something like that. Like sorry?
That doesn't have to be
I mean, of course. This is a left and a right.
you have 2 classes.
You have the
Yeah, so maybe something like that. No, maybe should do something like that.
Yeah.
Okay, good. Sorry. But then that's okay. So maybe so you're saying you can even know that the least common ancestor of them, one of them is the least common ancestor of the other. Right. But anyhow, the only problem is that there is an edge common to the two paths, to this path and that. So that immediately gives you a bound. Let's go to observation 1. So I want to make sure that gamma of I'm thinking of some event AUV, and I want to bound gamma of that event. Decide how many unknown variable it depends on, or how many events it depends on. But I'm going to, it's going to really depend on, first of all, what's the length? The AUVs are not all the same, right? It really depends on the distance between U and V, U and the distance. Right? When U and V get farther and farther away, there are more chances of depending on something else. So I'm going to kind of split it according to the distance between U and V, which is the same as the distance after factor 2, in the distance between these two. So maybe even before the observation, let's say for some event, or maybe actually differently. So let's AI. So these are all events in which the distance between U and V is like 2i, just to make sure that the distance between U to the least common ancestor is the distance in between, right? So this is just a hack, it's writing the distance of the least common ancestor about referring to the least common ancestor. Right, so I'm dividing all of the events to sets. Like siblings is one set, like our least common ancestor is our grandfather is another set, and so forth. And then, so the first observation is that if you take some A in AI, so A is like AUV, but I don't really care. So just take any event in AI, and you ask, how many neighbors does it have? How many things it depends on? But only in AI, because I want only in AJ, I want it as a function of the length of the avatar. So A is in AI, and I'm asking what can you say about the intersection of this set with AJ? A is in AI, and now I'm for any I in J, right? So I is the distance between A and E, and J is the distance between E. And I want to break it down according to these I's and J's. This is very asymmetric. That's what we do. So we definitely want a boundary. Remember, there is a product for all of these elements. Have to be a little small, so one is, yeah, we'll see. But you want a bound on that. And you can be smarter or less smarter here, but essentially you can bound it like very. So you just need to bound, you can fix A, so you have this fixed U and V, and the distance between here to here is I. And you ask, how many blue things I can draw of length J, 2J from one to the other, or J to this ancestor, that intersect in edges. Is you can be smarter or not, but it doesn't really matter. I mean, you should do something, but you can just say, for example, union bound over the number of possible edges. So it's like 2I edges. So here you just choose the edge. Maybe more edges, but it's union bound. Choose an edge or intersection. And having fixed that, now we need to kind of complement the path. And the edge could be on either the left or the right thing. And then you have to decide if, since this is the edge, how much you go down and how much you go up, and you can be very precise about that. But let me not be precise and just say like O to the J, A to the J. The reason being that instead of kind of arguing more in a tighter way about where this edge sits in this thing, I'm just looking at any length 2J path, whatever, and each time you have to, so even more so, I'm going to assume it's actually a length 4J path, not 2J, just so it will cover all possible ways that intersect the edge. Right? So it's 16 J. So it's still different. What? Wait a minute. Okay, so just call 16. Laziness. So it's at least 2. But, so what I'm doing is say that this edge, there is an intersection. So you fix this particular A, and now you're asking how many things in AJ are there that go through this edge. So now I should actually count or bound the number of length J or 2J paths that goes through that thing. And I'm lazy. So instead of doing that, I'm going to upper bound it kind of very loosely, but not too much. We give the same asymptotic result. We're just saying, well, every such length 2J path that walks through here, it could be that this is short and this is longer and so forth, right? And maybe this is the last edge, and then this will be longer and so forth. This will be longer. Instead of doing that, I'm going to just say, this is a length 2J path. A length 4J path will cover all possible ways. Like every length 2J path here sits in a length 4J path that goes to this edge, where you move down, like when you move down J. I don't know how many steps you move down here, but you move down at most J, and you move up at most J. So if this thing is at length of most, so you know that this thing sits in something which is of length 2J. And then there's the other branch. So I'm just saying 4J, even though public can say 2 times that. just a 4j as a safeguard. So this is definitely a bound on the number of paths of the 2j that goes through this edge. Probably you can make it 2 times a sum, and it goes over how many things you have below this edge. And but you know it's going to be at least 2 to the j anyhow. Just a calculation. Don't worry about it too much. And the second observation, one, observation 2. What's the probability of A for A is in AI? It's going to depend on AI. I want a bound on it. I want a bound on that and that because in a second, remind you the formula that we assume. It's going to require that this and that is small. So what's the? But it's also like intuitive because you want the bad events to have small probability and you want to have few dependencies. So what's the probability of A? Right. Right. So what's the probability of A? False, of course, means what's the probability you have at least half of the half matches.
Alpha by C up to I divided by 2.
Right. Very good. So what you did here, I need to add something, or multiply, or add this many times. But what you wrote here is if you fix the set of I over 2 indices in which they agree, this color agree, then for a fixed choice, maybe this choice, the probability of all of these pairs to equal to match is for each of them is 1 over C, and they're independent, so it's 1 over C to the I over 2. But now you have to also union bound over all possible, and you can do smarter things, but you should union bound over all possible places we match. So I need to multiply that. Right, so what's written here is it's a bound, not the exact quantity, but it's close. So what it says that I ask you what's the probability of A to occur, and the probability of A to occur means what's the probability they will have at least half as a fraction of the matches. And if I want to bound that, I can break it down using the union bound all sort of fixing the place of the match. Instead of talking about the probability of the union, I'm talking about the sum of the union. So, and fixing, this is one summary. And fixing a place. You have I choose I over 2 ways of doing that. Just choose out of this I, out of the pairs. And having done that, the probability that all of the other 2 will match is 1 over C to the other. And just before we go to break, just massage this a little bit. I'm going to, so in general, that would be, instead of that, like I choose one is delta I, you can do that. You can worry about the relation between delta and C, but let's not do that. Let's just bound this by 2 to the other. So quite close. 1 over square root I times 2 to the I. And if this is equals 2 to the I, then you can write it as 4 over C, it has nothing to do with the 4. Yeah. Now let me just remind you of the hypothesis. Once it holds, you know the none of the next one. As far as the probability, suppose this in general. It's in different letters because I don't remember what to do. And so you want, this is you need this. That's an assumption. If that assumption holds, you're happy. So I say one this. We want this to hold. Just then we don't know what the AXAs are at all. So we need to have some guess before we actually we need to commit a little bit about the explanation of X. So what do you think? I mean, as a function of I, the depth, right? So you have events sitting in different depths, like AIs. So what should you say about the dependency in I? Increase, decrease. I mean, you know that it's at least that. Because, I mean, otherwise it won't happen. Because you multiply the number smaller than that. And the probability of A, you see there, it decreases exponentially in Y. What kind of form of, what would you guess? I mean, you can have a parameter, but what's the behavior that you can apply? Again, you want this to be larger than that, that decays exponentially in Y. Let's examine that takes exponentially in Y. Let's call it k to the minus I. We don't know what k is, k is a parameter, we'll figure it out. But it makes sense. So this kind of relates to the question about what's the meaning of this. So it should be somewhat some upper bound, but on the probability, but it should also take into account those. So let's do that. Let's see. So let's just compute this. So what is XA for A in AI? It's just k to the minus I. Right, so this is x of that what we just said, k to the minus I. Now we need to multiply over all events that depends in this sense that we define on A, but let's also break it down to where this B sits, which AJ. Because we have different. So let's break it down, this product to products. All possible values for J, for the length of the other path. And then we are going to take all B in AJ. So we're going to take all B's in AJ, but they are also in gamma A. So we cover everything in gamma A. Then I need to write 1 minus x of B. And x of B, because it sits in AJ, so it's k to the minus j. So this is the right hand side. We will need to make sure it's larger than it. More precisely, we will need to make sure that we can choose the k. Okay. The right hand side. It's right, right? Very inventing things. No, but it's okay. So now it's just a matter of playing with it a bit. So what I want to do is to say, well, you know, what I want to avoid is to do it in one step. So first of all, let's bound this, but for which direction should we bound? I'm going to say that it's just one. Actually, I want to bound this from below. Because I want to show that this is larger than this. No, you're saying this is above the actually counting multiple above. Right. So actually I want to bound this from below, because if I bound this from below, then I know that this is out. And I want this to be out. Now we need to place to reduce rate configuration 1. Yes. So that means to say that this is less than 1. Is that why? Okay, but before I see understand. But before looking at that, yeah, I was playing for a second with this. I want to do it before after. So let's first bound this from below, and then because we know bound this from above, as you said, we're going to bound this from below. Good, I understand what you're saying. But let's first bound this from below, right? So just here's a useful tip. So 1 minus or plus. So 1 minus 6 is at most e to the minus 6. It's very useful. 1 plus 6. For x in 0, 1, at least, but definitely in 0, 1, which is our case. This is 4. But we needed the other bound. Right? We want to bound this from below. And so what you can do is you can take like e to the minus 2x, for example, and it works when x is not too large. So this, for example, we don't need that. I just can say. but it works when x is like small enough. Decimals. So I want to transform this to an e so that the product will become a sum. That's why I do that. So this is at least e to the minus 2, k to the minus 3. And that's just that part. And therefore, as you said, you take a product of stuff, each of them is, you have a lower bound for, but they're smaller than 1. All of them. So if you have an upper bound on this set size, you have a lower bound on the product. Because the more things you multiply, the more.
Some person, there's some negative values. That's also
Yes, right, same thing, right. Instead of talking about product that's smaller than 1, it's one of those negatives. Yes. But anyhow, this, it's at least, okay. So we have a bound on that, which is observation 1. So it's e to the minus 2k to the minus j times whatever is written there, 2i times 2 to the 4j. Right. Okay. Now I delete the bottom line. So now when you take the outer product of the whole j's, you get a sum. So the right hand side is at least, well, you have the k to the minus I sitting there, okay. But then you have e, and you should sum this over all j's. Maybe we should clean it a little bit. This is only 16 over k to the j. And you have a 2 for 2 reasons, e to the minus 2 and the 2 I from 4, and you sum over j. So it's a sum, j go from 1 to n, of 4i, k over 16 over k, to j. And this is the 16 over k to the j, 4i, minus, k minus. Yeah, you want to bound this from below, so you want to bound this from above. And this is just a telescopic sum. I mean, it could be a telescopic sum if we take k large enough. So if we take k, for example, to be 32, then the I doesn't really participate in the sum. So if we take k to be 32, for example, this is at least, which is 2, I, e to the minus, you have 4i, and this should be at most 1. Because the sum will be like upwards. And geometric, right, sorry. Right. Because this thing, I want to bound this from above. I can choose k over this. So I can choose k to be 32 before I goes outside. And then you have a sum, which is like 1/2, it's not from 1. So 1/2 plus 1/4 plus 1. So it's at most 1, close to 1. So the minus is at least. It's in the right direction. Okay. So anyhow, you can just, if you want to have a slightly cleaner way of looking at it, this thing, and you want this to be larger than the probability pay. And that's what we only bounded from below the right hand side to make sure that it's larger than the probability pay, which is this 4 over c to the over 2 that's appearing here. Right? So what we want will follow with what we want now. So we want that this thing a close game. Because this is an upper bound. This is a lower bound on the right hand side, this is an upper bound on the left hand side. What we said before. And you can do that. I goes away. Don't throw any eyes. Better go away. I goes away, and you see the number of colors is like crazily high. It's like a, you know, I don't know what the square root of 32. Square root of Newton's 4 squared. So there's a square here. Ah, it's squared. Oh, it's even worse. What the number? 32 squared times 4 into the 8. It's not 4. We have a 4. Okay. It's constant.
For n number of n?
That's what you want. Yeah, that's brilliant, right? Yeah. So yeah. No, static is the second thing. Static is what you're talking about. But then the question about this again, it's just for the purpose of talking about tree codes more than showing the non-trivial way of using the probability question.
Kind of lost. This one colors. What do we have?
A tree code with distance half. Because we choose the distance to be 1/2, where we committed to the I choose over 2. Otherwise, it will be I choose delta I. And then we calculated, the dependencies and the probabilities, and we chose a value for the XA for which this is satisfied, and that induces the number of colors. No. Yeah.
So this half means that at the worst case,
Right.
there are 2 vertices with half of the edges matching.
Right, exactly. So for example, for siblings, it will always be distinct, of course, otherwise it's 0. And for the next step, like at least one of them will be different cousins. Maybe I'm not good in this. I have a small family. I don't know. Yes, I don't know. I'm an only child. I don't know. I have no idea. I have one aunt. Yeah. Okay. So let's continue with the second proof. The second proof is much cooler, but it only, this Lovasz Local Lemma is quite general. And the second proof is really tailored to this specific question. But I want to give you an example where you use the specific question, like to structure the randomness, right?